Hurricanes create significant changes to coastlines. Dr. Meg Palmsten tells us how communities can get advance notice about threatening water levels. And the hurricane season kicking into high gear. Dr. Jason Sippel focuses on NOAA's new hurricane forecast model. This is NTWC Live. Q.
Good morning, everybody. Welcome to NTWC Live. It is Wednesday, the 19th day of July, already halfway through July. Good to see everybody this morning. Thanks for joining in on the conversation on our weekly webcast here on NTWC Live. Glad to have you along. Great program for you today. I think you're going to enjoy what we got to talk about with Dr. Jason Sippel and Dr. Meg Palmsten. It's going to be a good hour. It's going to go fast. I think we've got a lot to talk about today, so we'll get to that in just a moment. First, let's thank our sponsors who are part of this program day in and day out and have been for a long time. USAA. Thank you, USAA. All the programs we do at the Storm Science Network, the National Tropical Weather Conference, they've been a part of what we've done for a long time. So we appreciate USAA for everything you do. The South Padre Island Convention and Visitors Bureau, every year in the month of April, the National Tropical Weather Conference is live on South Padre Island. We encourage you to join us next April. We'll be at the Marriott Courtyard Hotel for NTWC, the National Tropical Weather Conference. Always a good conference, and the hospitality suite is always open there. Also, the Weather Company and Weather Boy, part of what we do here with this program each week, and we appreciate them. Weather Boy really doing some cool stuff for the National Tropical Weather Conference, bringing in college students, doing scholarships for college students from all over the nation to come in and give them basically a full ride to come to NTWC, and we appreciate that. So thanks everybody at the Weather Boy for what you guys are doing over there. Okay, big program today. We'll get to the tropical update a little bit later on. We'll have our GeoTrek segment, but for now, let's get over to Dr. Hal Needham, who is the extreme weather and disaster scientist with CNC Catastrophe and National Claims, to introduce our first guest and get the program started. Good morning, Hal.
Good morning, everybody. Beautiful day here on sunny Galveston Island. I'm so excited to introduce our first guest, Dr. Meg Palmsten. She's a research oceanographer at St. Petersburg Coastal and Marine Science Center. Really interesting work she's doing. Her work focuses on studying waves, currents, and transport of sand and other sediments causing coastal change on sandy beaches, with a special emphasis on making observations in coastal environments. She's especially interested in understanding model uncertainty and communicating forecasts to stakeholders and end users. Meg, thank you so much for taking time to come on NTWC Live.
Thanks, Hal. It's great to be here.
Meg, really interesting stuff. I mean, we know coastal flooding, currents, waves, it all has a huge impact on the coast. A couple questions we wanted to ask you. For one, when hurricanes threaten the coast, we often hear about the storm surge forecast, but what about wave heights? We sometimes don't hear about that as much. Who forecasts wave heights, and which stakeholders are interested in those predictions?
Yeah, thanks for your question. So first, stepping back to the first part of the question, wave heights are incredibly important when we're thinking about storms. In fact, wave heights are a key part of when we're forecasting coastal change for storms. So when we're doing that, we're looking at both the elevation of the tide and surge, which is what we're usually thinking about during storms, but then also the elevation of the waves at the shoreline. And we call that combination of the tides, the surge, and waves the total water level. We know that when waves reach the dune on sandy beaches, which is what I primarily study, that the dune starts to erode and sand starts to move offshore. And that's, the first level of the problem. But then as the total water level increases above the top of that dune, that's when you start to get water and sand pushing over the dune. And so whatever's behind that dune is now being exposed to water and sand and, the potential for damage. And then, of course, the worst case scenario is when the tide and surge gets over the crest of the dune, and that's what we think about with our really extreme hurricanes. And that's when the beach is subject to inundation and flooding, and we have the potential for breaching of the dunes, and even cutting a new inlet in an island can happen during that case.
Yeah, Meg, do you know, so does anyone forecast the total water level, or do researchers kind of have to piece together the wave height forecast, the tides, and the storm surge and kind of create their own?
Right, yeah, so to get to that part of the question, we partner, I work at the U.S. Geological Survey, we partner with the National Oceanographic and Atmospheric Administration, or NOAA, and work on their nearshore wave prediction system with them. And so what we do is we add a post-processing step to the nearshore wave prediction system. And we take the height of the waves and the period of the waves, so that's the time it takes a wave crest to pass a certain point, is what the period is. We take that information along with information that we curate about the local beach slope, And using all of that information, we can estimate what the wave height should be at the shoreline. And so we're able to produce that information. We produce it in real time, all the time. We do, in partnership with NOAA, a 6-day forecast. It's an hourly forecast, and we do that along most of the sandy beaches for the Gulf of Mexico and Atlantic. So anyone can go find that information. And then once we have that information, we can compare that to the elevation of features like the dune base or the dune crest on a sandy beach. And that will tell us about whether we're likely to have erosion or not.
Meg, so is that a USGS product then that comes out in partnership with NOAA?
Yeah, it's a joint product, so you can find it on the Nearshore Wave Prediction System website, and then we've got our own viewer where you can go check that out. You'll notice when you go to, actually, you had a question about stakeholders, and you notice when you go to our viewer that it's actually organized by National Weather Service forecasting offices, and that's because the original stakeholder for this forecast were the National Weather Service forecasters, so that they could incorporate information on coastal change into their daily coastal forecasts. Then as we had our viewer out there, we started to learn that we had other stakeholders who were interested in our forecast, and things as simple as people who wanted to know whether their beach volleyball court was going to be flooded one day or not, or people driving to work along a coastal road wanting to know if that road was likely to be overtopped with sand and water when they're going to work. So, not only during the major storms, we're thinking about coastal changes, when they can be very extreme, but even on a day-to-day basis, it might play a role in your life if you're living along the coast.
I could see those forecasts being really valuable. Sometimes people just assume that storm surge includes all of the water, and it doesn't, right? So you'll hear people say, oh, it's going to be a 6-foot surge. My house is at 9 feet. I should be okay. And they're not considering maybe the waves and the tides and different things. It sounds like you're taking all that into account with these data and with this viewer that y'all have put together.
Yeah, absolutely. And we're finding it's really important when you consider over the course of a year, what's happening. So we just published a recent study where we looked at our model results along the 3,000 miles of shoreline that we're producing this forecast for. And we found that when we looked over all of 2020 at times when waves were likely to be eroding the dunes, the waves actually contributed 73% of the signal to that total water level. So it's actually, can be quite significant during, the course of a year. Now, when you look at a specific, major hurricane, storm surge is likely to be larger than the contribution of waves. But when you step back and look at some of those other times when you have maybe a northeaster storm, or maybe you have a hurricane that's out in the middle of the Atlantic and it's not making landfall in the U.S., but it's still pumping those waves onto the beach with really long period swell, and that's contributing to that increased water level due to waves, and then the coastal erosion that follows from that.
Meg, I wanted to ask you one more question, and then I'll throw it over to Bill. He always has some great, insightful questions as well. And
Sure.
We'll also see, we have questions that come in real time online as well. Those are also interesting. I want to ask you, how does the research community measure sediment transport or erosion related to these larger storms like hurricanes? Like, are there research groups out there taking photos or measurements before and after the storm to compare differences? Like, how do we see how the coastline changed?
Yeah, absolutely. So this is a big part of my work, and also a number of other researchers at universities and other federal labs. So we can do this in a lot of different ways, and we can go from very small scale sort of point measurements all the way up to a global scale. So at the very smallest scales, we might do something like put an acoustic instrument in the water that's just sending a sound pulse to the bottom over time, and we can measure one single point through time. That's a really, researchy way of doing it. But that gives us one piece of information, but that's not enough. So another way we might study sediment transport and coastal erosion during storms, but we also do this during calm periods to see how the beach might be growing back after a storm, would be to go out and make a bathymetric survey. So bathymetry is like the underwater landscape, and to do this we would put a sonar on a boat or a jet ski, and it's like a fancy version of a fish finder you might have on your recreational boat. So go out and basically drive along and measure what the bottom of the ocean looks like before and after a storm. And then going up on the beach, so where we can, see the beach, we have stationary cameras looking at the beach. That's actually a specialty of my work, is using our USGS CoastCam network to look at those changes on the beach before and after a storm. And we specially calibrate our cameras so we can actually make measurements of change in the water levels on the beach. Then we also might take cameras and put them on a drone or an occupied aircraft and drive along the beach or fly along the beach before and after the storm. And we can use, again, those specially calibrated cameras and really detailed measurements about where that aircraft is located, and do 3D reconstructions of the beach. We're getting really good at this, so we're getting to the point now where we can produce information almost as soon as we can get an aircraft in the air. The processing time is going down as we're getting better at this. And so we're now able to incorporate some of this information into our real-time response. And ultimately what we want to be able to do is update our models right away after a storm. So that's something we're working on.
Meg, a lot of these things like the bathymetric surveys, I'd imagine those are maybe longer range projects that take a while to be funded and completed, and they're probably going around on year round. But then some of this other work, like deploying cameras, would you say like you may get teams out there the days before a storm hits to just really focus on that area of the coast that will be most impacted?
Absolutely. So the USGS has a really big effort. We have a group called the Storm Team, and we actually go out and put instruments out on the beach right before the storm in the area where we think it's likely to impact. So we're using information like our coastal change forecast and the National Hurricane Center forecast to decide where to place these instruments. And we might have a huge team before a storm like Hurricane Ian go out and put instruments out, deploy usually pressure sensors, sometimes cameras or wave buoys, and then that gives us all kinds of data to look at after a storm.
I've seen if there's a huge storm, you'll have sometimes dozens or even hundreds of these mobile tide gauge sensors or water level sensors that the USGS deploys. Really helpful for the research community to reconstruct what's going on afterwards.
Absolutely, we're really fortunate to have this group of people who go out there moving in the direction of the storm to put those instruments out and then get home safely before the storm arrives.
Meg, I wanted to pass it over to Bill. Bill, you always have some great questions. I'm sure you have some good insights and questions here for Meg.
Oh yeah, I'm fascinated with this sort of thing. It's really advanced quite a bit. I remember when I first started forecasting, one of our greatest laments was not having a sparse, just so sparse the amount of data we had on water level information after a storm. It was very difficult to verify what it is we were working on to forecast the storm surge. And that's what I've been mostly familiar with, is the tight information you guys are able to give us after a storm to fill in some of the gaps. So I'm curious, can you, off that same data, are you able to estimate observations of what the wave structures were like at those sites?
Right, so we do have some of our pressure sensors record fast enough at a fast enough rate to actually monitor the waves and that wave contribution.
Mm-hmm. Yeah, the models look great, but I always wonder how can you verify them when we're so hard to get observations of waves, especially in the beach environment in the storm, of course.
Absolutely. So those pressure sensors that the USGS Storm Team is putting out are an important component of testing the models, and then the cameras as well. So actually being able to see, as long as your camera is still recording data, to be able to watch that water come up across the beach is another really big component of the forecast. And we're constantly working to compare our forecasts to the observations that we make.
Yeah, the flybys before and after are always intriguing. It's very useful for us to make a quick assessment of the extent of the damage, how severe it was right on the immediate coast through those kind of photographic techniques. You think maybe that'll be transitioning into a drone operation as time marches on, or you think the aircraft will still be the way to go?
Yeah, so they they kind of can have two different purposes. With a drone, you don't usually cover as much area, but maybe you get higher resolution or longer dwell time to take more images. So that has value in one way. And then doing that same type of analysis on an occupied aircraft, you can cover hundreds of miles of coastline if you want to. And so I think both are really valuable, and we'll probably keep doing both of those things, I think, as a scientific community as we move forward.
Fascinating. The website where you have the viewer for this, do you have a link for that to give our viewers to how they can find that info?
Sure, I can maybe drop that in the chat.
Great.
Yeah, and go check out your favorite site to go to the beach, and you can scroll back through previous years and see old storms, or check out what it's going to be like today.
Yep, I always say I learn something new on every one of these calls, and that's my new one for today. I didn't realize you had that information available.
Great.
Online now. It's good.
Meg, I have a burning curiosity to ask you this question, and I apologize. It's self-centered because I live in Galveston, Texas. I'm behind the big seawall, and I've been wanting to ask you this. We know seawalls provide protection for the people behind them, but what are some other things they do, either positive or negative? Like, do they enhance erosion near them? Do they change sediment transport? I mean, are there other things seawalls do besides just protect people behind them from flooding?
Yeah, that's an interesting question. And it's interesting now, communities thinking back to the seawall in Galveston was put in place so many years ago. Communities now have this wide range of coastal protection, including seawalls, that they can consider. Other communities are thinking about beach nourishment and nature-based coastal management solutions, like dissipating waves through mangroves and salt marshes. So I don't have a specific answer for you, because I think it varies site by site and what's what other coastal management practices might be going on at a specific site. So I don't think I have a good answer for you today on that one.
It sounds like it's complex, though, and you have to consider not only seawalls, but just, I'd imagine, the beach profile, and like you said, mangroves, saltwater marshes. It sounds like these are really complex coastal environments that you have to model specifically.
Yeah, and so right now our forecast is focused only on sandy beaches, but we're working really hard on incorporating other environments. And so during Hurricane Ian, we recognized that we didn't have forecasts in coral reef line coasts, which are really important in, of course, the Florida Keys and other U.S. territories. And so that's the current direction of our research, is working on incorporating those coral reef line coasts. And so right now we're actually just recently published a new website where you can see for different hurricane scenarios what the impacts might be on the coral reef line coast of Puerto Rico. So we're working towards developing those real-time forecasts in some of those more complicated environments.
No, that's super interesting. It's fascinating to see the breadth of the work y'all are doing. So I know our viewers are really going to be interested to see that. Meg, I wanted to ask you something else. Last year, some of the hurricane forecast, some of the storms just left us in this position where there was higher than normal uncertainty, both in the track, but what may happen with coastal flooding. I know your research has looked a lot at model uncertainty. I mean, what can you share with our viewers about how to think about uncertainty and how to maybe take uncertainty and communicate that in the best way to listeners?
Yeah, so uncertainty is, I think it's all models have uncertainty, and understanding how people perceive uncertainty is really interesting to me. We know that no model perfectly represents what it's trying to forecast. And so scientists are making assumptions. There's different components of the model. We might not be able to measure all of those components precisely. And so when we're thinking about a process like wave run-up on beaches, like I do, we want to try and both incorporate what we think is important for the uncertainty and then communicate that. So if you actually go check out our forecast viewer, you'll see our forecast elevation for the total water level, but you'll also see an uncertainty band around that. And we think the largest source of uncertainty in our forecast is what we don't know about the beach, because that beach slope is changing from day to day. And so we try and capture that by looking at both for a specific site on the beach where we're making the forecast, how that beach slope has varied in space and time. And we know that because we've made measurements there, over the course of the last 20 or 30 years for most beaches around the US. And so that's how we're trying to incorporate uncertainty into our forecast. And I think just, for scientists and people who are, just looking at the forecasts made by forecasters, just recognizing that no one model is right. We need to look at usually a number of different models, or maybe the same model with forcing it in slightly different ways, and incorporating all of that into the forecast is important. And so I think it's a tricky thing, but really important to communicate. We've got the best available science, but it's not perfect, and so we need to always remember that part of it.
Meg, if you have a lot of uncertainty with a forecast, will you more share like the deterministic, like what the model thinks is most likely to happen, or will you share more of the worst case scenario and the chance that could happen, or will you share like several different angles on that?
Yeah, so we're trying to share all of it. So so that uncertainty band represents what we think is the sort of 5% worst case scenario, or the 5% best case scenario of the water level.
That's good. That allows users to kind of customize it for their needs and what they're looking at. Tim, do we have any questions that have come in online?
We do have a couple of questions that are coming in from online. Good questions as well. One is about sand getting into the storm sewer system, into the and is there a way that cities and communities can mitigate the impact that sand has when it washes into the storm sewer, into the drainage system?
That's a good question, and I don't know much about storm sewer systems, but certainly our forecast can provide the information on where that might happen. So when you see our forecast predicting overwash or inundation, that's a case where we're saying that sediment might be moving towards land, and that would be a case where there would be concern. So certainly we can look at where that might happen, and inform people with the best information we have on that to make decisions about what to do next.
In real time during the storm.
Yes,
that's fascinating.
Absolutely.
And another question coming in is about can we use your research to determine the safest places to build or not build? How we build, where we build, based on the research that you're doing and how the sand moves.
Yeah, well, the USGS is an unbiased science organization, and what we're trying to do is provide the best available decision makers for information for decision makers in communities, in the government to make those kind of decisions. So, we want to provide the best science, and then there it is to make choices with.
That's the ultimate goal, is to take your data and use it for the betterment of everything, right?
Absolutely.
Fascinating. Yeah, those are the questions that are coming from online. They've been really interesting this morning. A lot of chat going on back there, Hal and Bill.
Yeah, great stuff. Meg, any last take-home messages, if you had a minute or two to tell our audience, like one or two of the main things they should be thinking about with coastal flooding, with sediment transport? What are one or two of your main things that you like to share with people as like a take-home message?
Yeah, I think that just considering the whole range of storm surge, which we know is important, but also waves, and then how that translates into coastal change is really important. And we've got the information in real time, all the time, and especially during storms. So it's out there, and I hope you use it.
Yeah, thanks, Meg. Really, really great research y'all are doing, and I know our viewers are going to be really interested to check out that viewer and the different products y'all are putting together.
Great, thank you.
Thank you, Dr. Meg. We appreciate it. And stick around if you will. Jason Sippel is going to join us here after the break and talk more. And we encourage you to join that conversation as well. Great information, fascinating stuff. Thanks, Dr. Meg Palmsten, this morning. We appreciate that. We also appreciate our sponsors, USAA, the South Padre Island Convention and Visitors Bureau, the Weather Company, and Weather Boy. They make these programs a possibility week in and week out. So thanks to all of them for doing it. If you know anybody from there, tell them thank you, because they're the ones that are keeping this program alive week in and week out. So thank you so much. Hey, the tropics are somewhat alive today, at least in parts of the planet. Bill Reed, tell us what's going on around the globe today.
Okay, I'll do my best here. I'll share the screen here and put up the latest and greatest on what is going on. And this is Tropical Storm Calvin, which is impacting the Hawaiian Islands. They're getting pretty heavy rains on the east-facing slopes of the Big Island, and rain bands have been crossing the central and northwestern islands this morning as the storm, or what's left of it, it's well detached. Most of the active weather is way far from the center, which is down here, moving westward at a fairly good clip. By tomorrow, it'll be back to weather as usual in the environment down there. There is the track forecast. It shows by even this evening, the remnant effects will be pretty far away from them. Then we have Don. Don's been with us for, it seems like forever without really doing much. It now is showing its hand as its final act will be in the next 5 days to move slowly into the more northern latitudes and get picked up by the westerlies and merge with a frontal system further down the road. Satellite imagery, as you can see, it actually looks a little better today than it has in its lifetime as far as tropical characteristics. We actually have a little area of convection all the way wrapping around the center of it now. But again, it's going to be moving into a less favorable environment after today. And as Tim pointed out, we have a new little feature to pay attention to. Most of us have been talking about how unfavorable the open Atlantic has been for development, as is typical of July. And they see through us a little curve this morning and dropped a slight risk of a storm developing from a wave that came off Africa yesterday. As it gets into the central and western part of the main development region, it has only a 20% chance of developing. Satellite imagery this morning, it's hard to tell exactly, but I'm guessing that this is the feature with limited convection. Dry air and dust are the driving forces that are inhibiting any development chances as we go now. But maybe as it gets later in the week, it'll have some chance, so it warrants the development. The big dark area here is a dome of strong high pressure, creating a tremendous heat wave over in the Mediterranean region, not unlike the one we're having here in the U.S. Models, a different twist on the models this morning. Normally it's the GFS that goes nuts over something in the East Atlantic coming out that never materializes. Today it's neither of them are going real strong with it, but the European model has a more members of its ensemble, showing a system maybe trying to develop as it moves off to the west. There we go. Finally got it closed in. There we are on that. And I like this way of imaging it. It shows how warm the tropical waters are in a color scheme other than red and green. And the water temperatures in the tropics in general are about the same temperatures you would see in mid-September at the peak of the season, which is one of the reasons people are concerned that we think could get active very quickly if the dry, dusty environment were to break down and the easterly waves not encounter much inhibition as they come out to the west. So I think I'll stop it there. And I'm going to toss it back to Hal for an update on GeoTrek.
Yeah, Bill, thank you so much for the tropical weather outlook. You're really interesting as we're seeing things start to get busy. Well, hey, y'all, a quick spotlight on GeoTrek. GeoTrek travels the world looking for stories related to extreme weather and natural disasters not covered by the mainstream media. We're trying to do three things with GeoTrek: understand the physical processes behind extreme weather and natural disasters, understand their impacts on society, and then what we can do to get out ahead of these events and mitigate their losses to make ourselves safer and more resilient. Well, y'all, you're going to love this last episode of the GeoTrek GeoTrek podcast that we just recorded, you know, with so many billion-dollar disasters, we've realized we not only need to understand the physical science behind extreme weather, but also the social science. We have a podcast that just aired yesterday. It's podcast episode number 75 on the GeoTrek podcast. You can hear that on Apple Podcasts, Spotify, or wherever you listen to podcasts. It's a conversation with Dr. Laura Myers. So it's podcast number 75 titled Perspectives on Social Science for Hurricane Risk Mitigation with Dr. Laura Myers. She's a senior research scientist and director of resiliency at the Alabama Center for Insurance Information and Research at the University of Alabama. We really get into social science perspectives for how we can mitigate the losses of hurricanes. And three quick things that we shared with that. Number one, we talked a lot about the sociology behind evacuation messaging and how when people hear a message like you're under an evacuation warning or mandatory evacuation, they often don't run immediately to the car and hightail it out of there. They need a process where they're talking to their family, their friends, they're talking to other people. Are you evacuating or not? They may need 24, 36, 48 hours to kind of process that. And it may be on the third or fourth or fifth time they hear the message that they decide to get out. So we talked about the importance of these early evacuation messages because people need time to process that decision. Number two, we talked about vertical evacuations. The big focus with when hurricanes threaten the coast is to get people out of harm's way. But we talked about times when possibly vertical evacuations, people getting into hotels, high rises, multi-story condos could help save their lives. Storms like Hurricane Harvey in Houston, we saw water rescues of people nearly drowning, but in their background, we saw skyscrapers where people could get up above the floodwater. Laura shared specifically with Hurricane Michael in 2018 in the Florida Panhandle. They did an in-depth study on who died in that storm, and it was really the people in the single-family residential, those residential buildings, the small bungalows on ground level, those are the people that died, whereas the people that stayed, if they were in condos or hotels, they generally all survive. So we talked about ideally we get people out of harm's way, but if we can't, the concept of getting people up may work well, especially I think for South Florida, Metro New Orleans, and the Houston-Galveston corridor. We have millions of people we would need to get out of harm's way. If we had a rapidly intensifying hurricane, we may not have time to get everyone out of those areas. Vertical evacuation may be something that we need to start talking about in our long-range plannings. And then finally, Laura mentioned as her take-home message, people need to stay connected. Last year, we saw some shifts in the modeling and forecast changing from one day to the next. People need to stay connected. They need to have their notifications on, get your weather information from that trusted source or even multiple sources. But she mentioned the importance of people not seeing that early forecast, anchoring to it and disconnecting. We need to stay connected throughout hurricane season. And that was another really great take home message she had. Again, check it out. It's GeoTrek podcast number 75. I'll upload the link to our online NTWC live here today if you want to find it. But about every other week, we're airing a podcast that gets into understanding extreme weather, natural disasters, and what we can do to mitigate those losses. Really great to partner with NTWC this year, and excited now to get back to the rest of our broadcast this morning.
Thanks, Hal. That really struck an interesting disconnect for me after Alicia, and especially after Andrew. The concept of vertical evacuation was put back on the shelf because of the severe damage from the wind at the higher floors of these buildings. So it may be a good subject we can follow up on.
You know, Bill, something that hit me when I was doing field work in Hurricane Ida in 2021 in Southeast Louisiana, it was taking a very similar track as Gustav. Gustav was a Cat 2 in 2008, and there was a mandatory evac for New Orleans. Ida ended up making landfall as a Cat 4, similar track, but there was no mandatory evac. I know some of that might have been COVID and the complications with a COVID evacuation, but I think a lot of that was the rapid intensification. I think emergency managers might have felt like they didn't have time, that 72 hours to get everyone out of New Orleans. So with rapid intensification, I think vertical evacuation is something we should be talking about.
Yeah, it's a tough choice to have to make. Okay, our next guest is Dr. Jason Sippel. I've known Jason for quite a while, a fellow Aggie, and done well, I see, and he's enjoying life in Miami. His research focuses on improving operational hurricane forecasts through improved data assimilation. He also co-leads the Hurricane and Ocean Test Bed at the National Hurricane Center. One of the major focuses in leading the HOT, as it's called, is to improve the use and understanding of reconnaissance observations so that NHC can better assess tropical cyclone intensity and structure in real time. So with that, Jason, welcome to our show. And why don't you tell us a little bit about what it is you're working on?
So I have I've been a co-developer of the HAVS model, which is the new hurricane model that's replacing HWRF and HMON. And so there's a bunch of partners that have been worked on this, including several universities, several cooperative institutes, INCEP, the National Centers for Environmental Prediction, and our lab, the Hurricane Research Division at AOML in Miami. So I've been part of a very big group of people that's helped make this happen, and it was actually implemented at the end of, I believe at the end of June. And so right now we have the legacy models, HWRF and HMON, are running in kind of a diminished mode. INCEP is able to run them for a few select storms, but it's kind of conditional. They're not in their full force as they were last season. And now we have HAVS also running alongside those two models. So I do have a few slides. I don't know if you want to see the slides or if you just want to do Q&A. It's up to you guys how you want to move forward with this.
Why don't you go ahead, and if it's just a few slides, that'll give people a flavor for what it is we're working with.
Okay, so I'm going to share my screen. So I guess let's see if this works, hopefully. Uh-oh. Let's see if I can do this quickly. Here we go. Oops. All right, so I'm getting that Zoom will not be able to record the contents of your screen until it is quit. Is that okay? Let's see.
I've never heard that one before.
Do you mind if I log back in real quick to see if I can get this working?
Sure.
Yeah, that's fine. While we're doing that, we've shared some of the links for what Dr. Palmsten had to say. We've shared those on the live feed. If you're watching us live on our website, that information is there. Also, Dr. Howe's podcast, we shared that there during the interim here, so that should be there. So click on those links. I've clicked on most of them and already taken a look at those websites. So thank you, Dr. Palmsten, for sharing those. We appreciate that. Let our viewers see that. It's hard for the listeners to get to that, but the viewers, we can get them there. So thank you for that. We appreciate it. So, and we'll get Dr. Sippel back on here in just a second. I think he doesn't need to record, right, Bill? Because it said he can't record it, and that's okay. It's just a matter of sharing the screen, I think.
He may have accidentally hit the record button. It's right next to the share screen.
I wanted to say too, I think it's great that Meg and her team have a viewer. You know, when there's a product that you can direct people towards, it's more than just a concept. It's like, oh, when there's an active storm out there, people are going to have a place to go to see this info. So thanks for sharing those links, Meg.
Yeah, sure. I also shared our Coastal Change Hazards portal, which is where we put both of our real-time forecasts that are special during hurricanes when we're using National Hurricane Center models. And we also have storm scenarios, so you can look at worst case scenarios for coastal erosion for different category storms.
All right, we can see your screen now.
And if you're just real quickly, if you're listening to this on the podcast, go to our website, Storm Center Live. Hurricane Center Live, rather, and these programs are all there, and you can find the links there. So if you're listening, you can go to Hurricane Center Live and look at the old ones. You'll find it there. Okay, Jason, you're back, and we can see your screen. You're good to go.
Sorry about that. I have never experienced that before with Zoom. I'm not sure what happened. Okay, so I've got a few slides here. These are courtesy of Zanzang, who's the Fed in charge of the hurricane group at INCEP. These were actually some of the slides that they showed for the implementation meeting for the decision making for INCEP leadership. So a few things. Can I hide this? Yes. Can I? There we go. All right. So HAVS is part of the unified forecast system. Why is that important? Because the UFS is a framework being developed for all models at INCEP, where we're all migrating to essentially the same dynamic model. And one of the big problems we've had at NOAA in the past is we've had a billion different models that require different groups to maintain them, and all of them have been very different. And so what we're doing now is kind of moving to a common framework. So, for example, HWRF and HMON were totally very different models, and in upgrading them there's a massive overhead required for that. Further, HWRF had a framework that was really developed 15 years ago, and there was things that we just couldn't do with HWRF. So migrating to this framework, it's the same framework, it's the same model that the global model, GFS, is using, as well as other models. And halves A and halves B are both very similar in a lot of respects. They just use different physics, and I'll show you some of the differences. But it allows us to make advances more quickly going into the future. So that's really an important take-home point. Other than that, it's still, we have, HWRF had the coupled ocean and atmospheric and wave models, and we still have that in halves A. It's still have a wave model it's connected to. Halves B, they both have ocean models. I'll speak a little bit more about the configurations next slide, but some important points is we've done real-time testing for the last 3 years before this implementation. So we have solid results that were persuasive that this was the way to go. And as I said, we have two configurations, halves A and halves B, that will be implemented. Let's see, next slide. So here are some of the differences. So if you see blue or red, that's where the configuration between the two models is different. And I think the two big things is there's difference in the model physics, or there's three big things. There's a difference in the model physics. So halves A and B use different, they have differences in the way they handle the microphysics, which is the storms, the thunderstorms in the model, the precipitation. And then there's some differences in the boundary layer, specifically related to hurricanes. And so the boundary layer is the lowest, 1,000 meters or so, 1,500 meters, the atmosphere. So there's some differences in the way those two models are configured for those two types of physics. In terms of waves, so only halves A has waves. We talked about the importance of waves in the wave model in the last presentation. So halves A is run worldwide like HWRF, max of 7 storms. So all the basins get it, and it has the wave coupling in the North Atlantic basin. Halves B doesn't have the wave coupling, and it's run kind of like HMON, where it's only for the North Atlantic and East Pac. So here's the physics differences that I talked about here, related to the microphysics and the boundary layer. Those are the biggest differences. Some also smaller differences for the radiation and the cumulus convection. And now the big one, the results. So I think the biggest take-home message from halves is how much better the track forecasts are going to be from it than from our prior models. So this is the track skill related to HWRF. So right here, if you're positive territory, that means you're better. Negative territory means you're worse, and HWRF is the baseline. So how to interpret this is both halves models have about roughly up to 10% improvement at a lot of lead times. It's focused really between 24 and 96 hours, so days 1 to 4, 10% better than HWRF in terms of track. The intensity is also better. And it's all up to 10% better, but it's not as consistent. It's mainly halves B that's better. There's some consistency around day 2 between the two of them, but they're all in generally positive territory in the North Atlantic. For the East Pac, the track improvement is 5 to 10%. So again, we're still seeing that consistent track improvement. The intensity is kind of mixed, mostly neutral. Which is okay. There is improvement at long lead times, but this is kind of a common theme. It's really the track that improves the most. So we go to the JTWC basins. So this is the West Pac, the Southern Hemisphere. So West Pac is on the left, Southern Hemisphere is in the middle, and the North Indian Ocean. And so again, it's track for the West Pac. So the sample size is just, let me move this out of the way. The sample size is pretty small in the NIO, the North Indian Ocean. So I don't put a lot of weight into these results. But at least in the Westpac and the Southern Hemisphere, we got big samples. And look at this Southern Hemisphere, 20% improvement in the track. That's a really big deal. And intensity, again, it's neutral with some hints that maybe at long lead times we're seeing improvement over HWRF. So I think that is it. Okay, so concluding comments, HAVS is, again, part of the UFS, which streamlines development. So that, again, the important part of this is, not only are we seeing improvements in a lot of track, some intensity, but it's just easier. It will be easier to make improvements going forward. We have, with the same amount of people, we can get more done. And because HAVS A and HAVS B are the same model with just some different physics and maybe some different details, what you do in one model in terms of development applies to the other. So there's this overlap that is really helpful. But again, we see improvements. We're seeing, much better track forecasts, which I think HWRF was kind of notorious for having bad track forecasts. And so it's good to see that we're moving in the right direction there. So that is it in terms of my slides. So I will gladly take questions now.
Sure. The interesting thing, my take, it was always looking at the hurricane specific models as being our best path forward to improve on the intensity forecasting. And just one quick, I may be totally out to lunch here, but the improvements disappear as you go farther out in time, I would think, is probably because big changes in intensity are things like eye wall replacement cycles, rapid intensification, which are probably outside the realm of predictability at those time frames in our current science. Is that about right?
So I was trying to figure out how to stop sharing. So it turns out I've looked pretty carefully at the correlation between track and intensity errors, and it's actually winds up that the errors are not particularly well correlated. Where you do see that a relationship is when something goes really, really wrong, right? So if you have a really, really large error in track, it will affect the intensity. Or likewise, if you have a really, really large error in intensity, it will affect the track. I can't speak to why, at long lead times, the track improvements diminish somewhat over HWRF. I don't know the reason for that. I would have to look at the distribution of the errors. That was what I was showing you, was the mean error. So I would have to look at the tail and all parts of the distribution to better understand that. But in general, the track and intensity are not well correlated, except for when one goes really bad, then you see that.
Yeah, to me, the encouraging part is in that 48-hour time frame, you're getting definite improvements, and it was already pretty good. That's one thing to keep in mind. Yes, it's an improvement, but the forecast that it's improving on was also pretty good.
Yes, yeah, that's right in the watch warning lead time is critical. I think the one area where HAVS is not as good as HWRF that gives some consternation is with rapid intensification. The errors are a little bit higher than they were with HWRF. So that's something that everybody's aware of, and I have some known reasons why this is the case, and it's just going to take more computing at INSEP to fix the problem. So it's always more money, right?
Always. Do you go farther out in time when you run the models now, or is it still run out to 126?
Yeah, so now it's still through day 5, but there is active discussion about going through day 7. And just as the Hurricane Center is talking about, going to day 7 at some point, in the near future. So we'll have to do that. That's a reality we're going to have to face. The question is, how do you handle day 7 errors that are, 1,500 miles?
Well, maybe you can do it in a research mode, and only just display the 5-day until you're sure it's a useful product. Right.
Yes.
Hey, tell me about the HOT. I knew this was coming up. Jamie Roman given me a clue a couple of years ago about making space where the library used to be for a test bed in there. What all do you do in that?
So we had a great collaborative event last fall where we brought researchers and HSU specialists, and what it really enables is that one-on-one interaction between HSU and the researchers, and in this case it was really people that had instruments on the plane, and it was just a discussion about how to use the data that's coming off the plane and how to really even how to display it, because HSU, things are coming at the hurricane side, using that acronym. These are the hurricane specialists at the Hurricane Center. Things are coming at them a mile a minute on their shifts, right? They need stuff that's displayed in a really simple, neat, easy to interpret way where they can make an action on it. And so one of the good things that came out of that meeting was how to take the data that's coming off the plane and present it in a way that they can use. A lot of it was, in AWIPS, bringing this data into AWIPS and making changes. So AWIPS is the display system that they use at the Hurricane Center and the Weather Service. And so how to make changes in the display system so the data is interpretable. But there's also, we're moving in a direction where we just haven't made optimal use of a lot of the data coming off the planes. And we're moving in a direction. That's really one thing that I've been involved with is making those contacts with people that are working with the tail Doppler radar, with other instruments. There's instruments that display, that send wind retrievals, very high resolution winds below the aircraft. So that data is coming off the plane now, and the hurricane specialists are really interested in it. And so we're trying to figure out, how to use all this data in a way that makes sense, and that also helps the specialists to understand, nuances and differences, because sometimes the data can disagree. So what they're used to may not be, what is actually happening in a particular instance. For one instrument might be giving, like the SFMR, right? Everybody kind of is aware of the SFMR giving wind speeds that are, some people think are way too high, right? But now we have all these other instruments. If we have more data coming off the planes in a way that they can interpret, we can understand, well, are these wind speeds too high or not?
Yeah, it always is an interesting debate and challenge in the research to operations and vice versa mode of thinking.
Yeah.
Hal or Tim, what you got out there?
Jason, really cool to see these improvements in the models. I mean, where do you think the greatest improvements will happen, say, in the next 1 to 3 years?
So one of the challenges for HAVS was that it's a very good model, right? But it's also, because it's good, it's also very expensive. So it's just to run the forecast. I'm not talking about any other bells and whistles. Just to run the forecast was significantly more expensive than HWRF. So we didn't have the requisite amount of resources on the operational supercomputer to do some of the advanced stuff that HWRF did in terms of the way it was bringing in the reconnaissance data. So we had a big improvement in the model itself, but we had in some ways a little bit of a step back in the way the intercore data is handled. And so one of the big things we're looking at, in the next few years is getting that back, getting the data assimilation system to where HWRF was. And so if we can, and that I think is going to be really key to, I mentioned the rapid intensification. I think one of the reasons why the rapid intensification isn't as good in HAVS as it was in HWRF is because of that minor step back. So we get past that hurdle, we get the computing resources we need, then I think we're going to see a big improvement, and it's going to be reflected in intensity forecasts. Those kind of neutral-ish, not consistent intensity results above HWRF, I think we're going to be moving in a much more positive direction with that.
Thanks, Jason. No, that's exciting. I'm hoping we can. Tim, any questions coming online?
It's just a question about ensembles in an operational situation, not operational for halves. Are you running ensembles, or will there be ensembles?
So there have been ensembles run in research mode on one of the NOAA R&D supercomputers. I'm not sure that that's happening this summer, but it is something that is definitely on NOAA's radar. It's, this speaks to the issue that was discussed by the previous speaker about model uncertainty, right? How do you handle model uncertainty? And right now we're kind of in this unique situation where we have the legacy models, H4F, H1, plus halves A and B. So we have this mini ensemble, right? So, and that helps you kind of understand the uncertainty in the situation, and it allows you to message to that. But next year, we're not going to have H4F and H1. It's just going to be halves A and B. So at some point in the near future, and really to better communicate the range of possibilities in any given situation, especially this really is really helpful for RI, rapid intensification. We have to be able to run ensembles, and NOAA's aware of this. It's just a resource issue. How do we tackle this? How do we, at what point are we going to have sufficient resources to run, high resolution ensembles?
The funny thing that's been happening with the online questions today is there's about a 2-minute delay from the time we do this till the time it airs, and you're answering the questions before they ask them. That's happened 2 or 3 times this morning. So there were questions about dealing with rapid intensification. There were questions about looking back to see how accurate it's been. So you're answering them before the questions have actually been asked. So that's all we're getting from online. So Bill, Hal, do you have any final thoughts before we wrap up today's program?
Jason, you're saying these HAVS models can do great improvement, but they're really expensive. Bill, you're tied in with the golfing communities. Don't these professional golfers make insane amount of money? Can you connect and maybe have professional golfers fund this stuff?
All we got to do is get a cyclone in the North Arabian Sea, plow in Saudi Arabia, and
right.
That'll be the limit computationally.
LIV.
I'm figuring in the next 5 to 10 years, you'll have the computing resources to ensemble down to your scale, and then you'll be able. Then we'll see some really interesting. It'll just confuse old guys like me, but you all that are used to looking at the 1,000 lines on a map will know how to deal with it.
Man, Bill, I'm telling you, I 2030 timeframe, I'm very much looking forward to it, because not only are these changes in the data assimilation and the ensembles, these are kind of baked in. This is where we're headed. But NOAA's also getting more reconnaissance planes, and those planes have a big impact on the forecast, right? So we've got big requests, and some of the money's already been dedicated. Some is kind of on the way, I think, but having the capacity to use all this data more and get the planes in there more frequently, in addition to having just better models and better DA, I'm very much looking forward to where we're headed.
Can we schedule you for Wednesday, July the 22nd, 2030 for NTWC Live?
Hopefully I'm not eating my words.
Hopefully we're all still alive.
And then they'll be doing Zoom from the back end of a C-130. I assume that is the plane of choice for going ahead in the future.
It is. We're going to C-130, so we'll be more joint with the Air Force. The first one is paid for. We got a second G550, so we've got 2 G550s in the line paid for. You know what? I think now we've got both. I believe. I don't want to speak out of turn. I know we have one C-130 that's paid for, but I think the second one is also. And we're looking for trying to get 2 more. So, but the data impact, I've been looking at the data impact on the models, but also how well NHC does when there's recon versus when there's not. And the difference in the forecast quality is so great that I think it's persuasive to people that are far above my pay grade.
Well, I think my point was on all that back when they were trying to do away with it was that if we're ever going to latch onto the rapid intensification thing, we're going to need these platforms.
Yes.
Jason, could you maybe see recon going farther east?
That's actually one of the big. So we at NOAA, I'm aware that there's been Caribbean island nations requesting us to go further east. That's always a budget issue, right? So the current planes can only reliably go to about 47, 45 west, right? They can go further, but for any meaningful in-storm time, we can only task missions to about that far east of the islands. So that's not even halfway to Africa. So, I think we're going to have to, one of the things we're talking about, and I'm actively involved with, is using a combination of drones, and that was also discussed in the last speaker. How do we use unmanned systems, drones, along with the manned aircraft in a way that maximizes the impact of both, right? How can we use them, especially there's these long endurance drones now that can sit out for days, right? So I think where we're probably going to be headed is putting some of these out in the main development region, out between Africa and the islands, and figuring out a way to use them in a way that makes sense with the manned planes.
That's probably cheaper than my idea of building an island out there somewhere. Floating airport for recon planes in the hurricane season.
The NOAA aircraft carrier out there.
Actually, one of the things that NOAA did last year is we sent I think the P3 was the G4 out to the Cape Verde Islands, and I think that's a concept that we're probably going to use in the future, and especially until we get more drones and we figure out how to work that system. Is maybe sending some more flights out, especially if Caribbean nations are requesting the reconnaissance farther east. That would be one way to solve it. It would be nice in the future if we had a multinational effort, right, to do all this. But that's a dream.
A lot of ocean to cover.
Yeah.
We appreciate y'all. We're at the end of our time. It's 11 o'clock. When my dog jumps onto my lap, that tells me we got to quit because he has to go outside. So that's our time. Jason, Dr. Sippel, thank you so much. Meg, Dr. Palmsten, thank you as well for being with us today. We appreciate both of it. We've been sharing a lot of the links again on the website, on our website. So if you're listening, you can always go back to Hurricane Center Live, find this program, and look at the chat, and those links should be there. Hal, thank you, Dr. Hal. We appreciate your insight again today. And of course, Bill Reed, thank you for all you continue to do for the tropical update, everything there as well. It's been a good program today. We thank you for joining us. Thanks to our sponsors, USAA, the South Padre Island Convention and Visitors Bureau, the Weather Company, and Weather Boy, who all make these programs a possibility week in and week out. That's it for this week. We'll see you next Wednesday at 10 a.m. for another great program of NTWC Live. Until then, have a great week.
We hope you enjoyed this episode of NTWC Live Hurricane Center Podcast. If you did, head over to Apple Podcasts and leave us a 5-star review. And join us next week. This is NTWC Live.